of a kind introduction. So it's a pleasure to be here and talk about what we are trying to achieve with Invalid's collaboration and in collaboration with some theoreticians to provide an alternative way to look at genuine three-body interactions. So this picture here shows you which are our system of interest. So system composed of three particles, let them be baryons or mesons. And when you have three particles, you have mutual two-body interactions, but in low energy QCD, we also speak about genuine three-body interactions, which, if you want, is an artificial definition of the presence of intermediate resonances in systems like that, which are then translated in something which goes beyond mutual two-body interaction. And I'm gonna discuss with you whether it is possible to learn something new about genuine three-body interaction at the LHC. So in general, many-body system and the residual strong interaction which connects among them are essential to describe the property of nuclei and antinuclei. So indeed, the two-body forces alone are not sufficient to describe binding energy of nuclei. For hypernuclei, the situation is still rather unclear since data about hypernuclei binding energy are scarce. But the idea goes even a bit beyond that, because in principle, when you then think about an increasing baryon density, so when you go for nuclei, where nucleons are normally at distances of 2 Fermi, you go to more compressed matter as you create in a ion collision or as you might have inside neutron stars. Then clearly three-body forces or four-body forces, so whatever is beyond the two-body forces might become even more important than in nuclei. So that's why today the frontier to study the equational state of matter with high density and, for example, also strangeness content is trying to understand three-body forces because they play a very important role. And to provide you an example about how important these three-body forces can be when you have nucleons and hyperons, I show you a result which was published some years ago that is represented here in this figure, where you see the mass of neutron stars versus their radii. And each of these lines represent an equation of state. So we start with the green line, which is pure neutron matter. And you can see that this line goes through the measurement of 2 solar masses without any problems. Though when you add hyperons in the system, which is energetically almost necessary, so at high density, if you include only two-body interactions, as it is the case for the red line, the equation of state which results, it's too soft to get to the 2 solar masses. And you can change that by including, and in this work, the inclusion of the three-body forces was done quasi by hand, if you want, but such to reproduce the binding energy of hypernuclei. And you can see that this equation of state, if you introduce the three-body forces of type 1 or of type 2, transform itself into the blue line or the black line, which at some point, which gives rise to stiffer equation of state, up to the situation in which basically the three-body force, so which is repulsive in this case, compensate for the presence of hyperons, and then you land again on pure neutron matter. So equation of state. So this is just to say that knowing these three-body force is very important, and at the moment we don't know basically anything about the three-body interaction between an hyperon and 2 nucleons. Okay, so this is, let's say, if you want, one of the motivation to look into that, but let's see whether we can find a new observable apart from hypernuclei, right? So in general, the work we are doing within ALICE, and in particular in my group, is based on the femtoscopy technique, so which it's not new. I mean, Koning and Pratt actually already in the 70s developed a beautiful formalism, which connects particle emitting source created after hadron collisions with the relative wave function of two particles traveling with small relative momentum, and hence being able to undergo final state interaction. So basically, this is the master formula to understand this technique. Experimentally, you take pairs with of particles with a relative momentum k star in same event, and you divide by combination of this particle in mixed event. You clearly normalize and correct for eventual efficiency or resolution effect. And what Koning and Pratt put forward as a formalism is that this experimental correlation function can be translated into an integral, which contains a source function, which tell you basically, S for n star tells you the probability density function of finding two particles at a certain distance when a collisions occurs and when particles are created and travel then further. And then you have here a wave function, which is the relative wave function. And the trick here is that since the correlation function, as you will see in a moment, are characterized by very small value of k star, this wave function can be obtained by solving the Schrödinger equation for the two particles, and where you have a potential acting between the two particles. You for sure have Coulomb if you have charged particle, but you can have also a strong potential. Okay. So finally, just to make you an example, if you have now a potential, a local potential acting between two particles, here you see the example of repulsive interactions, so in red, and a partially attractive interaction with repulsive core in green. If you now map this potential into a correlation function, roughly what you will obtain are correlation functions which are between 0 and 1 for repulsive interactions, and for the attractive interaction, you see that the attractive part is mapped in a correlation function larger than 1. Still, you have here a little, I mean, a zone in which the correlation function goes below 1 because of a repulsive core. So our idea was to exploit PP collision at the LHC instead of looking at heavy ion collisions, because their sources should be smaller because the system is smaller. And if you have a system when you collide two protons, which has a side of around 1 Fermi, it is clear that also the distances at which particles are producing the star to undergo final state interaction will be small. So you have really the chance to investigate the short range strong interaction, which, as you can see in the potential sketch, it's seizable only below 2 Fermi, and then it disappears. So this is the main idea. Okay, where we do all these things, I mean, many people are doing this around the world. Personally, I work with the ALICE detector, and I mean, I don't want to tell you details about the detector, but the advantage of ALICE at the LHC is that it combines high rates of events that can be recorded with an excellent tracking and particle identification, meaning that we can reconstruct very efficiently strange hadron, charm hadrons, and then we can look at this interaction basically for any hadron pair combination that we want to look at, which is rather unique at the moment. Now, this source, now I showed you a formula in which the source is a rather reduced function. Often is considered as a Gaussian, but obviously the source does not only depend on the distance, but is a little bit more complicated object. And our approach to try to understand how to parameterize the source in PP collision was to use a data-driven approach. Indeed, what we know is that if you consider now the transverse mass of the hadron pairs, which is nothing else than the sum of the total mass to the square and the sum of the two relative, transverse momentum of the particles in the pairs. So it's a very important observables, because clearly if you have like strong, large MT, so pairs, we will basically where the transverse momentum of both particles is very large. You can imagine you will have at least a Lorentz boost. And when you look at the source in the pair reference frame, what you will see is that the source gets smaller, okay? So that's why we observe, and this without even considering possible additional, more complex physics phenomena that might occur in PP collision, like flow, for example. Yeah. Anyway, what we observe, if we take now PP collisions and PP final state particle, where we know everything about the interaction. We know the Coulomb, we know the strong interaction very well. So we can, if you want, extract the source. So, and what we observe is that the source present is MT scaling. So the larger the MT, the smaller is the source. You can see here for MT values around 1 GeV, you have a source of 1.4, right? For large MT or 2 GeV or 2.5, you have a source which is even below the Fermi. So this source, this core is the parameters, main parameter, the Gaussian distributions, okay? I have to say that in this work, we even considered in detail the effects of strong resonances, which obviously changes this source. And what we find out is that if you consider the effect of strong resonances, you have like a master source, which is the same. If you look at PP, proton lambda, if you look at pion, if you look at kaon protons, we tested several cases, and it seemed that this hadronization size, the MT scaling of this hadronization, let's say, source is the same for all hadrons. For U and DS quarks, okay? So what I wanted to say here is that we have a data-driven way to parameterize the source. So it's parameterized as a function of the distance and as a function of the transverse mass. And basically now, whenever you want to study the final state interaction, you just, for example, you want to study the final state interaction of a proton and an omega minus, which was not known before we look into it, and then you need the source. If you want to study the wave function, you just get it from this MT scaling, and then you test as we did the lattice calculations. Okay, so this was extensively done for many pairs, right? But and here you can see again how typically this density, so distribution looks like. So what you see here on the right hand side is the Jacobian multiplied by the source, which is in this case a Gaussian. So, and you can see that if you have a source radius of 1.25 Fermi, the most probable distance of two particles is around 2.5 Fermi, okay? And if you overlap this density distribution with a typical short-range nuclear potential, you can see that many of your pairs are eventually produced at a distance that is compatible, well, where the nuclear force is acting. Meaning, this shows you and motivates you why PP collision at the LHC, where typical source value of 1 Fermi are found, are extremely a good way to look at final state interactions. Okay, so now I'm going to show you what we did recently for three-body system. And our my first new results concern the correlation of kaon and deuterons and proton and deuterons. Now, it's again, at first sight, two particle correlations, but here the difference is that the deuteron is not a point-like particle. I mean, also proton is not a point-like particle, but actually the deuteron is composed on a proton and a neutron, right? And now what we did is first to consider kaon-deuteron and proton-deuteron correlations as effectively two-body system. And in principle, we thought, okay, we must be able to describe this system because we know about the Coulomb interaction. We even know about the strong interaction for these two combination, because if you look at this table for proton-deuteron and kaon-deuterons, there were a scattering experiment in the past which allowed people to extract scattering parameters. So you can see here for kaon-deuterons, K plus deuterons, you have spin average scattering parameters. You see here A0 is the scattering length and D0 is the effective range. Minus here for kaon and deuteron means that the interaction is attractive. So repulsive. So the sign convention in scattering theory is different for baryon-baryon and meson-baryon. So the negative sign for kaon-deuteron speaks for a repulsive interaction, while for proton-deuterons, the positive sign here means that on average, the interaction is repulsive for PD in both spin states, spin 1/2 and spin 3/2. But you know that in one channel there is a bound state because the helium-3 so appears for the S equal 1/2. Anyway, so what can one do in this case? One can use the Lednitsky-Lyubozhi approach, which provides a numerical formula for the correlation function. So instead of integrating the source times the wave function here, you assume a Gaussian wave function with a certain radius R0. And then if you have the scattering parameters, F0 now is the scattering parameter for a certain spin, and D0 is the effective range for this certain spin. You can really obtain an analytical formula where having the scattering parameter, you can produce a correlation function, okay? So, and this is the first thing we did because it should have worked, right? So, and yeah, I show you what is the result. So on the left-hand side, you see the K plus deuteron correlation function measured in PP collision, 13 TeV. These collisions have been collected with a 9 multiplicity trigger, just to enhance the number of baryon pairs. And what you see on the left-hand side is the correlation function compared to the green curve, which is the Coulomb only calculation done with Lenitsky. So assuming that there is no strong interaction, you see the Coulomb correlation is non-zero, but the data deviates from Coulomb. They are below Coulomb, meaning that there is a additional, so a residual repulsive strong interaction. And when you use the Leibnizky formula I showed you before with the scattering parameter, we have two sets of scattering parameters indicated by the two shades of blue, and you can see that both of them are perfectly on the data. I mean, the n sigma values are around 1. But on the other hand, if you go to the left-hand side, you can see that for PD, this doesn't work at all. So the blue, the blue curves show several calculations with different scattering parameters because scattering data were converted into slightly different scattering parameter from theoretical approaches, but doesn't matter what you choose. All the blue curves are scaled by a factor of 5 down. And I mean, the n sigma is 60, 50. So you cannot treat basically a PD system as a point-like system of, well, a system of 2 point-like particle. Why so? Well, because for KD, you know, the asymptotic shape of the interaction, which is repulsive, is the same even at short distances. There are no surprises. There are no feature of the interaction which show up only at short distances. You have a monotonic repulsive interaction. So the scattering parameter works because Lenitsky works basically because the asymptotic formula, the asymptotic interaction, so asymptotic treatment is sufficient. But for PD, this doesn't work. And actually, one could say, okay, maybe the source is wrong, but you know, the source that we use for KD, which is 1.4 Fermi, it follows exactly the same MT scaling I showed you for two bodies. So So this gives us some confidence that if it works for KD, the same idea that we have for KD should work also for PD. And so for PD, then for the calculation, we use a source of one Fermi. So now the question is, what has PD that KD does not have? Well, the deuteron is a composite object, so it contains a proton and a neutron, meaning that if you have a proton and a deuteron close to each other, they will undergo Pauli blocking. So meaning if a proton sees the structure of the deuterons, right, which should be the case if distances are short, you have to consider Pauli blocking, which Nenitsky doesn't know anything about because he considers two particles point-like and distinguishable. Moreover, the PD system is complex and the asymptotic shape of the interaction is repulsive, but if you put three nucleons at short distances, you have you have partially attractive interactions, so the system is much more complex. And so that's why the picture of 2 point-like particle doesn't work. And as I will show you, in order to reproduce this PD correlation, you need a full-fledged three-body calculation. So you really need to consider the deuteron as a composite object of a proton and a neutron. And this is exactly what we did, starting a collaboration with theoreticians in nuclear particle physics, so which have at their disposal the full-fledged three-body wave function. So here indicated by psi M2 M1, when M2 M1 are the quantum numbers of deuterons, so formation, and then the relative quantum numbers between P and D. And now, how do you calculate a correlation function in this case? So we followed in this case the Mrobczynski approach, where the correlation function of PD multiplied by the probability of forming a deuteron AD is nothing else here than this integral, where you have the three source function of the three nucleons, and then the wave function, the full body, so the full three-body wave function projected on the initial three-nucleon state. So here AD is the formation probability, which contains detail of the wave function about the deuteron. So meaning that inside this AD, we need to plug the correspondent full-fledged, let's say, wave function of the deuterons. We use either the AV18 wave function of the chiral effective Fitzgerald wave function. And here you can see how then the final formula to calculate this PD correlation function looks like. And you can see that basically this three source function, I mean, it has been shown in this work by Mrobczynski, can be approximated with basically one effective Gaussian, where the parameter is the distance between two nucleons. So this Rm is nothing else than the effective radius that you would measure even if you have only two protons, or a proton and a neutrons. Okay, so we do this game, and actually a new paper on the theoretical calculation has just appeared on the archive, and this is on the left-hand side the result. So what you can see here is that, well, the calculation have been done by colleagues in the theory department in Pisa. And the calculations here showed in three versions. So you can see you have like the Coulomb only, including also anti-symmetrization. You have the S-wave only calculation, where this S-wave is an S-wave between the proton and the deuteron. And then in blue, and then you have in red the full-scale calculation, including S-wave, P-wave, and D-wave. And you can see on the left-hand side that the shape of the correlation function changes, that actually S-wave only is very different from the case where you include all partial waves. On the right-hand side, you can see now our data, and you can see that already comparing by eyes, we are kind of getting closer to the data. And now a little bit of more detail. So imagine now that you do a full-fledged calculations, but you use only a Born approximation for the interaction. What does it mean? That you the calculation contain the anti-symmetrization, but you consider only the part of the wave function which is asymptotic. So if you want, you do a little bit of cleaned up Lednitsky. So you do a Lednitsky with anti-symmetrization to see whether this is sufficient to reproduce our data. Now, the results is shown by the orange curve, which compares the data. And you can see in the lower panel where the number of sigma is showed that this Born approximation is not sufficient to describe the data. While if you look on the right-hand side where the full-fledged wave function is included, you see that the red curve perfectly matches the experimental data. And actually, if you would do the calculation only including S wave, here shown again by the blue curve, again, the number of sigma, shows you a clear discrepancy. So what does it mean? So basically that deuteron can be used to study three-body states. So if you combine them with the third particle, and that at LHC, we are sensitive to the short-range part of the interaction. So this asymptotic description is not sufficient because, well, it doesn't work because it doesn't know about the structure, but even if you include the anti-symmetrization, so you include partially the structure, but if you consider only the scattering parameter, so the asymptotic behavior of interaction, this is not good enough, okay? So, and the question which one can ask is, okay, all these full-fledged interactions, so the full-fledged wave function contains mutual two-body interaction, but it also contains three-body interaction. So now, what happens if I switch off the three-body, genuine three-body interaction? Do I see a difference in the correlation function? So the question is, am I sensitive to the presence of the three-body interactions in this correlation function? And this plot gives you the answer to this question. This is the ratio of the correlation function with the three-body interaction divided by without. And you can see that the effects are depending on K star and they are very small. And at the moment, if you consider the radius of 1.4 Fermi, which characterize our inclusive measurement of PD, you see that you have difference up to 2%. The statistical error and the systematic error are not sufficient to see this effect yet. But more statistic has to come. So factor 600 is being recorded as we speak, actually. And especially if you then select PD pairs with larger MT, you can go to smaller value of radii, so from 1.4 to 1 Fermi, and then the effect becomes larger. And I am confident that we can see a 5% effect in the future, meaning that so far we just see that we see short interactions, but deuterons, they reserve a lot of surprises for us now that finally we know how to treat their physics in a complete way. And this is the first work done in this direction that explain really carefully the shape of a correlation function. What we did additionally is to go and look at triplets of particle not bound. So, for example, 3 protons and 2 protons and a lambda. When you look at triplets, obviously the correlation function change a bit shape. You don't talk about K star anymore, but you talk about Q3. So you project so the relative momentum of the 3 particle on one variable at the moment, because statistic doesn't allow you to do more differential study at the moment. So here you see the formula for Q3, where the Q, E, J are the relative the invariant momenta between pairs. And also in this case, so like we can try to do the extension and say, okay, if we have now a 3-particle correlation, can we connect the 3-particle correlation to a 3-body interactions? So clearly here, this is the hypothesis which needs to be tested, that you have a source that is not yet fully investigated yet for 3 particles. And then you have a wave function for 3 particles. And this wave function will contain mutual 2-body interactions indicated here by the green connections, and eventually also 3-body forces, so genuine 3-body forces. And now the idea is now to show to you how well can we do from an experimental point of view so far in order to really look at triplets of unbound objects. So these are, I want to show you first the measurement to show, first of all, that with Alice detector, it is possible to look at this kind of correlations. And here you can see proton-proton lambda correlations for as a function of Q3 on the left. baryon and antibaryon are summed up because the strong interaction doesn't differentiate between particle and antiparticle. We think on the right-hand side, you see triplet of protons. And the first thing you should see is that, first of all, you see a signal, which is already very good, because, and you see a signal which goes down to Q3 values of around 100 MeV over C, which is a very good value. And this plot shows you that these triplets measurements of 3 baryons are possible at LHC, okay? And these are run 2 data, and run 3 should allow us to achieve a factor 600, I think, in statistics, because we have specific trigger for that. Okay, but now we measured this, and now we would like to understand a bit better. So, and what is the question that we can ask ourselves? Whether these correlation functions, which are not flat, contain only mutual two-body interaction, or if there is something more, okay? And in order to gauge this something more, we applied cumulants in femtoscopy. Basically, this is a method normally used for flow harmonics, where basically you want to extract the genuine, in our case, we want to extract here on the left, the genuine 3-body correlations. And in order to do so, we take the, we want to, so the genuine 3-body correlation is here on the right after the equal sign in red. And what you measure, although, is a 3-body correlation. And now, Kubo put forward this idea that if you have a 3-particle system, you can decompose it in a genuine 3-body correlation plus 2-body correlations, permutation, so lower order, plus single particle contribution. Okay, so if we would be able to analytically, let's say, write down these 2-body correlations, we could try to see whether by subtracting the 2-body correlation from the measured 3-body correlation, which I just showed you, we see something which is not 0, basically, right? This should be the first smoking gun. So, and as you can imagine, we did that. So we evaluated this lower order contribution, and there are 2 methods to do that. The first one is data-driven. So you basically use event mixing. So you take 2 particles from one event, and you take a third one from another event. And then basically you combine event X with event Y, and you obtain in this way a partially mixed correlation. And this correlation gives you, if you project it on Q3, gives you the expected 2-body interactions, so for a certain pair. But we actually developed also an analytic model in my group. Actually, Rafael Del Grande, Laura Fabbietti published last year so-called projector method, where basically we calculate the projection. So we perform a kinematic transformation of a 2-body interaction, in the case R region, to a region, so to a correlation as a function of Q3. Meaning that you go from pairs to triplet. So for one Q3 value, basically you have a full phase space, right, for K star. And you just basically integrate over all possible. So you integrate over this phase space, right, and you project, okay? These 2 methods are equivalent. The right method is just like for us to check that we understand the physics and everything is under control. And I'm show you that now. So if we consider lower order, now the 2 correlations that you see on the left and the right are only the lower order correlation, meaning that the data are obtained, so the data are the blue points, and those are obtained with a data-driven method, so mixing pairs of one event with triplets of another event, while the gray curve shows you the projector method. So, and you can see that these are equivalent, and that the projector method allows you to extrapolate to Q3 equals 0, right? To make prediction also in this region. So it's a nice control tool to see that you understand the physics that is going on, right? And now, basically, we want to compare the measured 3-body correlation with the expectation from the lower order. So what you see here, so the pale greenish is the measurement, right? And in gray, you see the lower order. So now, if there is overlap between the gray line and the data, so in green, it means that there are no cumulants. I mean, there is no non-zero cumulants. And on the left-hand side, you can already see with your bare eye that statistical and systematic uncertainties are huge. So although it seems that the experiment lies above the gray line, this sensitivity is basically too small. So you cannot say, I mean, the statistical the confidence level is basically does not allow you for any evidence, right? So we have like an accordance of a couple of sigma. But on the right-hand side, there is this one bin, which shows a huge deviation. And if you now convert, if you look now not at the correlation function, but you really subtract the lower order and you look now, you have on the y-axis not C, big capital C, but you have really like the cumulants, right? C is small c3 is really the cumulant. So if this is 0, it means there is nothing beyond mutual two-body interaction. And if it is above 0, below 0, you see a smoking gun. And you can see that for proton-proton lambda, the statistical significance is 0.8 actually even, meaning it seems that for now we cannot say anything about a genuine three-body interaction. But for proton-proton-proton, the situation is different because the statistical significance of the deviation, although it's only one bin, is 6.7 sigma. And in order to check whether this effect is just like, an experimental effect that we don't have under control, we also analyzed triplets containing 2 protons and 1 antiproton with the same method. And you can see here in red that this control sample, where we don't expect any three-body genuine effects, is perfectly compatible with 0. So meaning we see three-body effects in PP. What is that? Most probably is Pauli blocking at 3-particle level because the 3 protons, they don't like to be together. So, and this is something which is beyond like mutual two-body correlations. But actually there is probably also an effect of 3-body strong interaction or long-range Coulomb interaction. We actually do not know yet because in order to quantify this, we need a full-fledged theoretical calculation. And this is on his way because Alejandro Kiewski from the PISA group, who also did the calculation for PD together with Michele Viviani. Now is calculating the correlation function for 3 protons. Here you see some preliminary calculations. So basically what you should look at is this right-hand plot where you can see, if you compare it to the full wave function, full correlation function that we measure, it's similar, but the features, so there is a deviation here for small Q3, but okay, one has to see when the calculation is really final and we have an apple comparison. But clearly, again, these measurements that we are doing, which are possible, they put a lot of pressure on the theoretician because now they are, let's say, called to calculate a 3-body system, unbound 3-body system, which is something that nuclear physics didn't do so far because the data were not there. Okay, I came to the end of what I wanted to tell you today. I was showing you the first measurements that we tried to tackle the problem of genuine 3-body interactions. So I showed you PD, how we need a full 3-body calculation to describe this system. Then I show you that it's possible to measure unbound triplets of 2 protons and 1 lambda, and also triplets of protons. Clearly here for the PP lambda, imagine that the round 3 data would confirm this attractive interaction, so not the repulsive one, which people now need to keep all this picture of hypernuclear bonding energy and equation of state and neutron star together. If we would discover an attractive interaction, this would completely change the way we look at interaction. So this would, produce a lot of entropy. I sincerely hope it is the case so that maybe we find something new, really new. And I didn't speak about that, but we look also at other systems like triplets of 2 protons and 1 kaons. in the same spirit of looking at triplets. And here you can see the results, which are now published in a paper recently put in the archive, where although errors statistic is better than for 3 baryons, but the cumulants are at the moment compatible with 0. So we need also there more data to understand eventual presence of 3-body forces. But okay, for that, I hope to be able to, me or somebody else from my group, to tell you more about that in a couple of years once we are done analyzing run-free data. Thank you very much for your attention.
Thank you so much, Laura. Well, that was a lot of, looks like a lot of work, especially that 3-body stuff. So does anybody want to just unmute and ask some questions? Well, let me, I'll have a bunch of questions, but I'll give people, oh, yeah, go ahead, Nu, just unmute and speak up.
Yeah, Laura, thank you for this talk. I have a question. I think it's on page 14, when you discuss the theoretical calculation.
Here?
Yeah. 14, yes. My question is, in the model calculation, do we know the source size used? Is this number consistent with what we would guess?
I mean, in the model, we put in the source size, because basically, you know, this parameter Rm is something that we put in because we measure the nucleon source, the effective source, right? So obviously we have to take care that the MT, MT of the pairs is correctly accounted for. So plug in 1.4 Fermi.
So it's a 2-body source size you put in.
It's a 2-body source size, yes, because this Morovshinsky approach is following. You produce 3 nucleons, basically, and short distances, right? And then you have like, so, and then at some point, a deuteron is formed. There is a certain probability of form a deuteron, and then they, at some point, depart. But clearly, the correlation function keeps the whole history of the interactions, right? Once the nucleons are produced, then they start to interact. At some point, they stop. You don't see anything anymore because they diverge. They are too far away. But, you know, so it goes from a 3-body system to a 2-body system. But, so what we show in the paper, which should be out for quark pattern, is that, I mean, our data, they look compatible with the description of a system where the degree of freedom are nucleons at short distances, at the same distances as we measure pairs.
Okay, thank you.
Okay, let me ask a question about, well, just first to make a comment. These correlations, you have the 3-body correlations. Those numbers are gargantuan. They're like 10 to 20. And could you show those again without the, before you did the subtraction of the 2-body effects? I just
so these are the correlation here.
So these are the both PP
genuine
and PP lambda.
So these are the naked correlation, if you want, like
native, the native. Okay, and that's so PP lambda has and then after you correct for the, how high does it go after you correct for the? So that goes up to about 5, and then there's the 1 point with the big error bar. How
then you go. Should I go to the cumulants or should I say here?
The cumulant ones. I just wanted time to digest it again. It was just it was a lot to think about.
This is the cumulant. No, sorry. This is
cumulants on the PP. The cumulant is still up. Okay.
Yeah, because
at the same point, the one that goes up. Because the Q scale is different. Okay. I just want.
So the Q scale is different, but look, this is a super huge error, right? So if you sum it up, this is not even 2 sigma. Yeah. So it's for 1 beam.
Okay, so that first point that's near 5, where is that on the other curve?
I can
on the one with the cumulants. So that one is
one. Okay.
Yeah,
okay.
this one. Where is that on the other curve?
I go there. I maybe have to clean. Wait.
It's Oh,
is around 2.
okay, so so it's that second point there. Okay.
Yeah, this is
where
would be
your
this
0
point.
was
So
moved on the 2 curve, where the, okay.
yeah, it goes
so, but
down
it's
a
still-
bit,
it's
but
still
you see
2.
it's compatible with 0 at the moment. So you
Okay.
need, you see, you have the statistical significance is 0.8, so not even close to a signal. I think what it's important here is that we can measure it. We can go down to 100 MeV over C and we can measure. And if now there will be something significant, we will see it now end of this year already, because we will have factor 100 more of statistics already with the data of 2022. But then to interpret this, you know, in a full-fledged three-body, this is, I don't know, when in if, yeah.
Okay. Well, that would be interesting if that really held true, because that would be very significant extra bit of interaction.
Yeah.
And I'm not sure this idea of how, you know, making cumulants, if that works when the correlations are larger. I mean, if they're a little 2 or 3% correlations, it makes sense. But when the 2-body correlations, if they're significant, then I'm not sure it makes sense to think that you're getting the 3-body part by.
I agree with you completely. What my claim is not that by measuring the cumulant, we get the genuine 3-body interaction. No, but we have a smoking gun. We have a smoking gun. We have a feeling whether there is something or not. So you know, whether you see something beyond mutual 2-body or not. This is the only claim we do.
I think that what really needs to be done is for the theorists to address this is to really do a true 3-body calculation.
Absolutely.
Extremely non-trivial.
I know, but
there's a pretty big investment on their part.
I know, and this is the reason why they didn't do yet. But my hope is that once we will show them the beautiful data, at some point people will be motivated to do this very expensive calculation. Yeah.
Okay, Zachan.
Hi. Well, I just have a naive question. So when we pick 2 particles to calculate the correlation, how do we actually isolate them from the potential interactions with other particles?
Well, the thing is that you don't need to, because you know, obviously in these multiplicity events, you produce on average 30 particles, 40 particles, all at small distances, clear. But these are ultra relativistic particles. So and all of them have relative momenta, which normally are large. I mean, only a few per mil of the statistic has small relative momenta, right? Both K star and Q3. So most particles have relative momenta, which are larger than 200 MeV over C. So they fly apart from each other very quickly, so they don't undergo any strong interaction. So you don't see it basically. And how do we know it that we don't see it? Because we looked at all possible known interactions, so proton-proton, pion-proton, kaon-proton, you know, where you know the interaction, and we don't see any disturbance by other particles, because clearly, if you have a triplet which is collimated, this third particle could participate to the interaction, but this is such a small fraction that on average, when you select pairs, you just see the effect of final state interactions. All the studies we do for 2 particles obviously have errors which are around between 5 and 10%. Okay, so this is not a precision experiment. So, but within the errors we gauge, these effects are completely negligible. Yeah.
Okay, thank you very much.
If I can throw in something there about your question. The reason in interferometry why you can sort of imagine that 2 particles after some point interact only with one another is that you are only looking at very small relative momentum, and that you're in the limit of small relative momentum at some point those particles will only see one another and the others will be separate. And you're also assuming that the interactions with other particles are basically, randomize the momentum distribution when they happen. And that is as you get to larger Q, this assumption that you can factor out the rest of the system and just do this wave function weighted Kuhnen formula becomes let's say more and more questionable. But it's an uncontrolled approximation. It's not known how good or bad that really is.
Absolutely. I mean, the only control that we have is that by measuring all the known interaction and trying to see whether the scheme we have with the source and so on matches, So, and this is what we do. So it's not, it's not an analytical approach, so that tells us how much, but it looks really like these effects are negligible.
Yeah.
Okay, thank you.
Okay. Any more questions? Otherwise, I have some more.
Yes, I have a question. It's Maria Stefaniak. So first of all, thank you. It was really nice presentation and discussion. And I have I think, quite general question. So I saw some results from other experiments and also from Alice of proton-deuteron correlations, but this was like heavy ion collisions, and they were still using this like two-body approach to parameterize the function and to learn from it. And is it because this is like a heavy ion collision and this is PP, or what is your opinion about this?
So no, thank you very much for this question. So in heavy ion collision, as you might know, sources are larger, much larger. Depending on MT, they vary from 5 to 10 Fermi, basically. And I'm talking about R0, the Gaussian parameter, meaning that distances can go between 10 and 20 Fermi. Then at these large distances, the asymptotic treatment of a wave function is completely legit. You don't even care about Pauli blocking anymore, because really deuteron and protons are on average at certain distances that only the asymptotic part of the interaction matters. And in that case, it seems to work. You are right. And that's why, but in PP, when you have particles are closer to each other, then this asymptotic approach is not sufficient. And this is why, and it took us now 3 years of work to understand what is really going on. So because there were very precise measurement of deuteron, proton, deuteron, triton correlation at AGS in the 90s, very beautiful data. But back in the days, people took Lednitsky and described the data with larger sources, basically. They fitted the sources because they did not have the idea of employing a full-fledged three-body calculations for that. And also they did not have this source model that we have with all resonances and things like that. So now the work was really to show now that you need a full-fledged three-body calculation, even if you have deuterons in PP collision, which is a pain, but it's also an asset, because this allows you, now PD, the interaction is known, right? But what about deuteron lambda, right? Deuteron lambda, nobody knows. Nobody knows how lambda PN works, but we will measure this at short distances.
Okay, thank you a lot.
You're welcome.
Okay. Anybody else? Has enabled? Okay. Anybody else with a question? Just speak up, because I'm not seeing anything, and I'll ask or make mine is more of a comment, long comment. So please, if you got questions, pipe up. Okay, so now you mentioned this, Laura, and I think you were maybe saying the same thing, and I wasn't sure. But if you go back to the one of your very first slides with the Kuhnen formula, okay. Yeah, so you have a wave function in this formula, and what the Lednitsky formula does is it replaces the wave function with the asymptotic form and then uses that asymptotic form all the way to R equals 0. Now, the asymptotic form is good as soon as R is big enough that you're outside the range of the potential. Say proton, you're beyond 1.5 Fermi, and there's no more interaction, and you just have the asymptotic wave function with a phase shift. And what the Lednitzky formula does, it assumes that asymptotic form and projects it all the way to 0.
Yeah.
Now, if so, it gets the part of the wave function inside the 1.5 Fermi is wrong. Now that's fine if this is a very small fraction of the overall source, because the source is very big, like in a heavy ion collision, like you said before. But for a PP, the whole Lednitzky thing becomes quite bad, and this is especially true for PD. And the reason it's especially true for PD, you're thinking of a proton and a deuteron. And remember, the deuteron, the proton, and the neutron are 4 Fermis apart. And so now if the second proton comes in, it starts to feel an interaction a long way from the center of mass of several Fermi away. And so I would say the Lednitzky approximation is not only poor for about anything in a PP source, it's absolutely horrific for PD. And
I agree, but but the reason why we show it and I discuss it is to make it clear.
I'm not saying as criticism, but you should.
No, but many collaborators also criticize it. But the reason why I'm showing is you are completely right. It's just like to go step by step, because this 3-body calculation is extremely complicated and extremely, I don't know, not so easy to digest. And that's why, as you said, Lednitzky projects, basically extrapolate to small distances. And what I find beautiful is that for KD, it works perfectly because basically the asymptotic behavior can be extrapolated to small distances. You don't mind, right? It works perfectly.
I will share a screen with you. And I also want to point out that if you don't necessarily need a 3-body calculation to do the PD, if you're using the whole wave function. And here, just a second.
Should I stop sharing?
I think I can do it because I'm a co-host. Okay, and I'm going to share this. Okay. Okay, did that show, or maybe it didn't?
Yes, we see an animal, I guess.
Do you see 2 plots side by side?
Yes, and
okay.
found Veggie
these are the proton-deuteron phase shifts, experimentally measured.
No, we don't see plots. We see
you don't see the plot. Okay, never mind. It did. Let me do the new share. Why did it not do?
Preview, maybe.
Share. There it is. Okay, gotcha. There it goes. Okay. So the stars, the left figure is just the experimentally measured phase shift with the stars. And what I did was I took those experimentally phase shifts and I just designed a potential. I just made some things with step functions and stuff that fit those phase shifts. Okay. And then I took that phase shift on those potentials, solved the Schrodinger equation, and did the whole Kuhnen formula. And then the resulting correlations are shown on the right. And once you count that, some of the source will be uncorrelated, it looks, I've looked at this with some other, I'm not illegally, but anyway, it looks like it will do very well. But with the wrong size of the source. In PP collision, we can never have a source of 5 Fermi. Oh yeah, then you'll bring it in a little bit, but anyway, this is what you would get if I'm not sold on the fact that you necessarily need the 3-body problem.
No, I am sure that we necessarily
anyway, it would certainly be better, but you can.
I think you need, because these radii, they are not consistent with what you find in K on deuteron. K on deuteron, the radius is 1.4 Fermi. It follows the same MT scaling as all pairs that we have.
Okay, well, I don't have this compared to data, but for heavy ion stuff, we looked at some stuff and it looked pretty reasonable. Anyway, my only point there is that if you get away from the Lednitzky and you do the full wave function, but without going 3-body, you will get something that is not. I'm not saying it's as good as the 3-body calculation.
Yeah, okay, I understand what you say.
That will be much more reasonable.
Yeah, okay, I understand what you say.
Okay. Let me unshare. Okay. Any more questions out there? Okay. Well, Laura, thank you very, very much. And
Thank you for having me.
okay. And Maria might email you with with some invitation for you and your group to more of you to join our little bi-weekly HBT discussion.
This would be fantastic. I would really very much like it.
Okay.
Yeah.
Okay. Okay. Well, in that case, I will close down shop and thank everybody for coming. And
Bye-bye.
special thanks to Laura. Thanks so much.
Yes,
Thank you. Goodbye.
Bye.
Bye-bye.